Hello everybody! We find ourselves here at the Technical Faculty of the University of Erlangen Nuremberg. My name is Jörg Franke and I'm head of the Institute for Factory Automation and Production Systems. It's a great pleasure to me to invite you to the Research and Innovation Event Week, which we organize together with our most important cooperation partner, the Siemens AG. The Institute FAPS, which we call it, has two sites, one in Nuremberg and one in Erlangen, and this is the research lab in Erlangen. And now I would like to invite you to come into the research lab here in Erlangen. And now put on your virtual reality glasses and follow me through the virtual lab tour.
Well, thank you, Professor Franke, for this very warm welcome of today's event, and sorry for briefly interrupting you. But before we start the virtual journey through the lab together, I would like to briefly introduce myself as your moderator today and present you what lies ahead of us in today's event. My name is Markus Schober, and together with my team and colleagues from Siemens, we are coordinating the Siemens FAU Research and Innovation Ecosystem Erlangen Nuremberg. With today's lab tour, we do not only want to show how the factory of the future might look like, but also discuss what composes it. Therefore, we switch in our agenda between live demonstrations of drones, autonomous intralogistic systems, robotic systems, and exciting research project pitches. But now, I give it back to Professor Franke first, who will introduce us to the exciting research areas of the Institute for Factory Automation and Production Systems at FAU.
Ladies and gentlemen, dear cooperation partners, dear friends of the chair. My name is Jörg Franke. I'm head of the Institute for Factory Automation and Production Systems since 2009, and together with my approximately 120 employees, I research innovative manufacturing processes for mechatronic products. The overarching goal is to link the various sub-functions of a factory into a computer-integrated overall concept. The Friedrich Alexander University Erlangen Nuremberg, also known as FAU, is the second largest university in Bavaria and one of the few full universities in Germany. We have 5 faculties and cover a comprehensive range of subjects. For us, a part of the School of Engineering, it is therefore very easy for us engineers to link up interdisciplinary and to closely integrate further competencies. For example, from the field of medicine, psychology or ethics into our projects. This is probably one of the reasons why FAU is one of the most innovative universities, ranking 14th worldwide in the Reuters ranking and first in Germany, ahead of the TUM and RWTH Aachen, for example. Within the Department of Mechanical Engineering, there's a vigorous connection to manufacturing technology, and as part of this department, FAPS takes a strong interdisciplinary approach. The interdisciplinarity is also reflected in the industry-oriented focus of the chair with 8 research sectors at 2 locations. The electronics production research area is dedicated to the manufacture of mechatronic systems in 4 key areas. The focus is on power electronics, printed electronics and optics, innovative SMT production and 3D MID technology. In the context of these focus topics, the research area deals with the relevant technologies such as additive manufacturing, packaging and interconnection technology, or end-to-end digitalization in order to increase the efficiency and reliability of electronic components. Electromechanical engineering in this research area of electrical engineering focuses on the production of electrical machines. Here, the main topics, electrical conductor as well as magnetic materials and their processing, are addressed in a fully comprehensive, future-oriented and sustainable manner and validated on the basis of the rotating electrical machine, the electric motor, and the stationary electric machine, the inductive charging pad. Wiring systems. The research area Wiring Systems deals with novel concepts for efficient signal and power transmission. Onboard power supply systems are comparable to the blood and nerve circulation of a human being. To master the complexity of these assemblies, holistic data models are generated along the entire value chain. From this, innovative systems for worker assistance and automated assembly of cable systems for future mobility concepts are realized. The eHome Center researches solutions for self-determined intelligent living, taking into account economy, ecology and social needs. In the Living Lab at the Auf AEG site in Nuremberg, research activities are brought to life in the form of a showroom. And then the medical technology research sector. Here we transfer the know-how acquired in industry to this highly innovative sector. In particular, we are dedicated to researching novel mechatronic therapy systems, digital replication of biological structures and properties, and digitally supported process optimization on the medical supply chain. In our research projects, we are characterized by interdisciplinary collaboration with users from medicine and industry. The research area Robotics aims to further develop robotic systems. The first core area in mechatronic components, where, for example, the new types of compliant actuators, multimodal sensors and kinematic concepts are being researched. Furthermore, the focus is on software, framework for communication, autonomy and interaction. In addition to technology-related content, superordinate questions regarding human-technology interaction and acceptance, context-related safety and standardization are considered. The subject matter includes all forms of robotics, from industrial robots through professional and consumer service robots to social robots. Automated production systems. The focus here is on research topics in the context of commissioning, operation and optimization of automated production facilities and cyber-physical production systems. The research fields are addressed in 4 key areas. The control technology and sensor technology focus deals with hardware-related control technology topics. The focus on industrial communication covers all aspects of vertical and horizontal integration. One of the largest focal points is software and IT in manufacturing. Aspects of plant commissioning, the design of industrial service systems, and the integration and use of AI applications in an industrial context are located here. The focus on factory energy networks and energy efficiency is relatively new. Here we are working on the implementation on the DC factory and smart grid approaches for manufacturing. Engineering systems. The research sector Engineering Systems pursues the overarching goal of providing a fully digital representation of complex mechatronic systems as part of efficient and integrated engineering. To achieve this goal, the colleagues use an interdisciplinary approach, which includes the complete virtual planning, design, simulation and control from the idea to the initial commissioning. An interdisciplinary exchange on cross-cutting technologies take place in the technology fields and links the scientific staff across the research sectors and locations. The technology fields are organized dynamically and address current trend topics. There are currently 10 technology areas covering different process-oriented or methodological approaches. The goal is to sustainably establish and further develop jointly used technologies and methods, e.g. in the area of AI and ML, in which the FAPS chair has developed into one of the strongest research institutes at FAU. FAPS covers application-oriented cutting-edge research in all areas of factory automation for mechatronic products. If you want to get to know us better or have a fascinating research idea, don't hesitate, get in touch with us.
Thank you, Professor Franke. And now it's the time. Let's put on our virtual reality glasses for the lab tour. Sebastian Reitelshöfer, who leads the research group Robotics at FAPS, will guide us. So please, Sebastian, can you bring us into the lab?
Thank you, Markus, and a very warm welcome. Herzlich willkommen here at our laboratory. I'm very pleased to have you here, and together with my colleagues, I'm really excited to show you some actual research demonstrators and projects in our group. As I said, I'm really excited. We are all excited because we are doing this live. So hopefully the demonstrators will work. If not, you can at least see that it's not fake. But hopefully we will see a perfect working of our systems. So as I already said, we are here in our laboratory in Erlangen, one of our 2 facilities, and within this lab we are doing research on complex mechatronic systems, on robots, on assistive devices, and on systems related to medical technologies. Today we want to focus on intralogistics and autonomous systems that can do tasks that were hard to automate some years ago. But hopefully within the next 2 blocks with 15 minutes each, we can show you some projects processing or proceeding a little bit into a nearer future of manufacturing where systems can interact and interoperate. Today, I and my colleagues want to show you 3 demonstrators in more detail. And first of all, we will start with our autonomous flying robots, and my colleague Markus Liert will, after the short introduction, give you an insight on the flying systems. They are a fascinating class of systems because they are quite new, and in terms of industrial usage, there is a lot to do, but Markus will tell you something about that later. And the second project, or the second group of topics we will have a closer look in the second block, will be mobile autonomous systems. There we have, I would call it more or less a zoo of very different intralogistic systems of different size, different capabilities, and I will try to explain you some of our research topics while showing you the systems. And then the third demonstrator, or the third station in our lab tour, will be the remote operation of those systems. So why did we choose those three projects, those three project classes? Because they really nicely tell a story on how to further develop autonomous systems for usage in factories and in all kinds of professional applications. Within those research fields, what is a common point there is that we all use software frameworks to realize those functions. So all of the systems you will see, all those systems heavily rely on a robotic framework called ROS, and we use this to not only do research, but very recently also to somehow try to shift to a industrial application. So we see first applications of those frameworks for real products. And secondly, it's a nice storyline because you can see a really early stage of a development where we are probably some maybe years away from a real productive usage in factories. And then we will shift to floor-bound systems, which probably all of you already know or even use, but one can identify very interesting research topics there as well. And by being able to autonomously move around and to change locations, we are able to do fascinating, complex tasks. And hopefully, if we are doing well in our research, those autonomous systems will make their tasks in, let's say, 90% of the day. But even in that very optimistic case, there's 10% in a day where they will need help. And therefore, on the third stage, the intuitive interaction with those systems, we will show you how to help and how to interact remotely with complex mechatronic systems. So this will be our lab tour. And for the first part, I will now hand over to Marcus, and he will explain you something about our flying robots.
Okay. So thank you very much, Sebastian, and a warm welcome from my side as well. In the first virtual demonstration, we will show you a use case where you can see our autonomous drones or autonomous flying robots in action. Before we switch to the demonstration, let me give you a short overview on how we can achieve the autonomy that is required for our systems. As we fly indoor, we have an indoor localization system. We do not use GPS, but we have an ultra-wideband indoor tracking system that is capable of locating our drone with an accuracy of around about 10 centimeters. Besides, we have various kinds of sensors on our drones, mainly cameras. The cameras are used for environment perception, to locate objects, to detect humans, and to adapt the flight behavior to gestures, for example, that are performed by the humans. A quite unique point of our systems is the charging system. Of course, for autonomy, we need an automated charging system. You can see the charging system on top of the drones. And compared to other systems, our system is capable of docking to the charging station from underneath. So it is actually hanging on the ceiling instead of standing off the ground for charging. Why do we want to dock our systems to the ceiling? For example, if we have now a sensor system attached to the bottom of our drone, it then can perform stock taking actions, it can monitor the environment, and so on.
And this actually brings me to the various fields of application that we use our autonomous flying robots for. On the one hand, it is stock taking. For example, we fly through a high bay rack and locate objects, determine the positions. We have also systems that are capable of interacting with various objects, that are capable of placing sensors or detecting cracks in ceilings or walls. And one of the main systems, one of our main research areas is the autonomous transportation of various cargo. I think we can therefore now switch to the live view of our demonstrator. And before we actually start the demonstration, let me talk a little bit about what we'll see within the next 4 to 6 minutes. You can now see the live view. You can see our flying robot hanging in the charging station in the top left corner. And you can see in the middle of the camera view the blue small load carrier that the drone will now grasp autonomously. It will then transport the load carrier to the robot. The robot will locate the load carrier, grasp an object, and place it in the other load carrier. The drone will then return to the charging station. So I hope everything is ready. My colleague has a thumb up, so we can start the demonstration. Okay, as you can see, the engines are started. The system is now undocking from the charging station, and it has received the task to locate the load carrier and to grasp it. It is now approaching the load carrier, and we have a camera on the underneath of the drone, so it can locate the load carrier, stabilize its position in relation to the load carrier, and then slowly descend to grasp the load carrier. As you see, it has now landed on the load carrier. Now the load handling device locks the connection between the drone and the load carrier. And after we validated that all systems are working well, then the drone will take off again and transport the load carrier to our manufacturing station. You can see it in the top right corner. The UR10 robot is waiting for the load carrier to be arriving. As soon as the drone has received or has reached the destination, it will deposit the load carrier on the landing spot. You can see now the drone is always trying to reach the destination with a certain accuracy. That's why from time to time it can take a little bit longer. But for all tasks, we need a certain accuracy. That's why we need to ensure that the flight position is well. The drone will now return to the charging station and have an eye on the robot. The robot will in parallel grasp some object from our small load carrier. Within the small load carrier, we have some suites, and we have a simple neural network to locate the suites in the box. It will then grasp the object using a suction gripper and just place the object from the one small load carrier in the other load carrier. The drone, in the meanwhile, is docking to the charging station, and now the batteries can be recharged. So we have a fully automated system. So as we talk about live demonstrations, you can now see that the object detection has failed, and our gripper was not capable of grasping the object. But I think everyone will believe me that this is working and quite state-of-the-art. So you can imagine that we have grasped an object, and now the drone will receive a second task to collect the load carrier again and transport it to the warehouse where it can be stored again. So the drone is undocking again. now again approaching the destination at the robot. It will now again stabilize its flight position above the load carrier that is standing at the robot. As soon as the position is stabilized, it will again be scanned and then grasp the load carrier. Again, the connection between the box, the load carrier, and the drone is established, and we can now transport our load carrier to the given storage position. As you can see, the box is placed in the storage position, and the drone can then return to the home station to charge the batteries again. Oh. Okay, well, speaking about live demonstrations, it seems it wasn't capable of actually approaching the station, but you all have seen the process once. And what we could saw in the live demonstration very well, it's why we cannot buy such systems yet. For example, we do not have any global redundancy in our localization systems. And that's a point that is quite important for industrial applications. We need to ensure that the system is working reliably. So one of our main research points is also to achieve a triple modular redundancy, so that in future there is always a fallback system, so that even in the case of a malfunction, the task can be proceeded and we can operate safe for human workers that can be in close distance to the flying robots. So that was our first live demonstration. I think we can now switch back to the presentations, and we will see each other later for the second live demo from our laboratory.
Thank you, Sebastian. That was very exciting. Wow. As promised before, in the next few minutes, we will take a closer look on several selected joint research projects between Siemens and FAU. During the research project pitches, you are kindly invited to ask questions via Slido. You can find the Slido window on the Siemens event page next to the live stream. It might be the case that during the first part of the lab tour, some questions have already come into your mind. You can just write them also in the Slido right now, and we will answer them in the final Q&A session at the end of today's event. But now to the research project pitches. When considering the factory of the future, interdisciplinary aspects are particularly important. Thus, in today's first research project pitches, Fabian Hartner will elaborate on digital platforms in the manufacturing industry from a business perspective. And Petar Vukovic will explain us in more details simulation options of industrial communication networks during the planning phase. So enjoy it. Please, Fabian, the stage is yours.
My name is Fabian Hartner. I am research assistant at FAPS, and I will present you my current research project together with Siemens Technology on the topic of digital platforms in the manufacturing industry. If we look at the value of the 50 most valuable companies in Europe by market capitalization, they are currently valued at 3.8 billion euros. This includes very well-known and long-standing companies such as L'Oréal, Linde, Shell or Novartis. In comparison to that, just the 8 most valuable platform companies have a value of 8.1 billion euros. platform companies such as Microsoft, Amazon, Apple or Alibaba have managed to become the most valuable companies in the world in a relatively short time. This success of the platform business models is attracting attention in all industries. Now the question is, how can such platform business models also be created and established in the manufacturing industry? To answer this question, our research project together with Siemens Technology is focused on creating a fundamental understanding of these new platform businesses. But first of all, it's important to differentiate between two perspectives on platforms. On the left side, it's a technical perspective in which platforms are seen as technical products that support companies through a modular structure. This can appear digital, such as Linux, or physical, such as a construction kit. Addressed topics are, for example, the use of technology, cloud technology, software interfaces, or hardware architectures. But on the right side, platforms are seen from a business perspective. Here, platforms act as intermediaries that connect two or more players and enable them for further interactions. This perspective addresses value propositions, market dynamics or business relations between different roles and is, in our opinion, very relevant for the success of platforms and is thus focused in our research. So, what is the big change through platform business models? Traditional value creations take place in linear value chains. Typically, a product is manufactured or processed and then sold to a customer in a supply chain, like in the automotive industry. The economies of scales are critical, as the cost per product can be reduced if a larger number of units are produced. Transactions between the two business partners take place directly in a one-by-one business relationship. In a platform business, there is typically a central platform owner. This owner defines the membership rules, governance and platform strategy. Since he enables and coordinates the transactions, a value network is created by him in which different roles can participate. To simplify different platforms, here you can see a typical transaction platform with providers and requesters, like on Airbnb, for example. With these roles, so-called direct network effects can now arise with a role, for example, that with more users on Facebook, more and more users are joining. In addition, indirect network effects can arise between the suppliers and requesters, so that, for example, with more providers on Amazon, even more buyers also join Amazon. Together with Siemens Technology, we are now exploring 4 areas of these platform businesses. First, we try to better explain the terms used, such as platform economy, digital platforms, or platform business, so that there's a common understanding of them. Secondly, we want to explain and systematize different platform types. For example, a classical marketplace, an intermediary, or an IoT platform have different characteristics and need to be distinguished and explained. Third, our platform research addresses the characteristics of the manufacturing industry. Previous research primarily addresses the private consumer sectors like Uber or Airbnb. However, since a B2B business is much more complex, we focus especially on these characteristics. The last aspect we address in our research is the platform business dynamics, like the network effects I just mentioned. In particular, we explore the dynamics that can occur in different examples of digital platforms, especially in the manufacturing industry. Overall, the project goal is thus to explore, analyze, and better explain the topic of digital platforms for the manufacturing industry from a business perspective. In this way, we want to achieve that there's a better understanding in the industry. In addition to the successful B2C platforms, we hopefully can establish and support the creation of successful industrial B2B platforms. Thank you very much for your attention. If you have any questions, you can always contact me. Thank you very much.
Okay, thank you. So do you have any questions? I couldn't read any question in the question and answer session, but you're welcome to write me a question. Okay, so there's the question, where do you see industrial platforms go in 5 years? So I think the B2C platforms I mentioned are like a few years ago, a few years ahead. So like we could see Amazon or Google, they are very relatively established in their industries. And now since 2-3 years, more and more industrial B2B platforms are starting. And so I can see right now that there are many platform offerings are starting. And now it's the question who is surviving in the market. Some of the platforms are already closed already. So I think in the next few years there is a lot of ongoing to-dos, and also it's perhaps the opportunity that one platform is growing or another one is growing ahead. So there's a possibility, and I think there is a lot to do and a lot of possibilities that are not just mentioned yet. So I think it's interesting also in the next 5 years to focus this topic. So we will see. So the next question is, why didn't you include Siemens in the list of platforms? So during my project together with Siemens, we are also including the Siemens projects and Siemens platforms. So the most famous one like MindSphere, but also other kind of platforms that are also have the characteristics of a platform business model. We are analyzing them and have also and discuss them with the employees. And so, but if you have any more examples, you always are welcome to contact us, and we can together analyze your business and also your platform kind of business. So the next question is, what will be the key factors for a B2C platform to be successful? So for B2C platforms, there are a lot of success criteria, and it's always depending on which kind of platform you mention. So there are the typical sharing platforms, like you know it for Uber, or when you want to share any kind of your car with your neighbors. So these kind of platforms have different characteristics and different success criteria in compared to when you think about your smartphone, Google Android, or such examples. So in the B2C context, also in the context of Amazon, the success criteria are researched very well in the last years. And there are a lot of articles about discussing different success criteria. And now there's the big question, how can we transfer it to the B2B in the industrial context? And here it's not too early to say that there are a few success criteria. So we focus on having a look at the B2C success criteria and thinking about how can we transfer them to the B2B context. And it's not always easy, because the B2B context and the industrial context is not the same. So you have not like a few thousand or million people joining your platform like in the B2C context. So there are just mostly a few companies who can join it. So you have different aspects, and also you have different aspects in complexity. It's interesting to see what are the really success factors in the industrial environment. Okay, so I think I can't read any more questions. So thank you for your questions. So you're always welcome to contact me. I'm also on the website of FAPS. You can always write me an email if you have any questions or if you want to discuss the topic. We are very open to analyze also different platform examples or just to discuss the topic. So thank you very much for your question. And now I'm pleased to pass on to my colleague, Petar Vukovic, and his presentation about simulation of industrial communication networks. Thank you.
Yeah, dear ladies and gentlemen, my name is Petar Vukovic and I'm working as a research assistant at the Institute for Factory Automation and Production Systems. In this presentation, I would like to introduce to you our cooperation project with Siemens, in which we are investigating the simulation of communication networks already in the planning phase. But first of all, I would like to show you the motivation by using the life cycle of a production plant. The life cycle is divided into 5 different steps: design, planning, engineering, production, and service. And of course, there are already simulation tools that validate industrial communication networks, but these tools all start late in the life cycle of production plants. And therefore, early errors often remain undetected, and errors are more expensive the later they are discovered in the life cycle. And for this reason, in our project, we are looking for a way to start early in the life cycle and perform a simulation of the industrial communication network as early as possible. To realize this, we developed a possible simulation process. For this, we relied on already existing tools in the development so that the additional effort is as low as possible. This also reduces the degree of complexity. The process is divided into 3 different main components: plant planning and simulation based on plant simulation, communication network simulation based on Omnet++, and both tools are widely used and known so far in the industry. And for the data exchange between 2 tools, we use universal tool independent format. In order to take the dynamic aspect of a production into account, a permanent data exchange between both tools must be established. To ensure that the necessary data from a proper network simulation is available as early as possible in a life cycle, we rely on the information in the asset administration shell. For this purpose, we have extended the asset administration shell with a communication simulation model to include all application-dependent data. In plant simulation, this information is added as extended library and then instantiated. This information exchange is realized by using XML or JSON. And in addition, plant simulation then offers the advantage that information becomes dynamic through the production flow and thus optimally reflects the real communication flow. And this transforms plant simulation into a reactive asset administration shell. For the data exchange between 2 tools or between these 2 tools, it is important to us to rely on already existing industrial standards. In addition to the data exchange, should also be a tool independent so that the data can also be available for other tools. And that's why we chose Automation ML, because the standard is growing in the industry and also has a dedicated modeling for communication networks. We can also extend the standard beyond this for our own purposes. When integrating the data later, we can decide independently whether to use the optional data or not. To ensure that the dynamic data is also included in the network simulation, we need a co-simulation. A co-simulation between the 2 tools is therefore required. In plant simulation, the dynamic data, such as status of the machines, paths of the HEVs, or positioning of the network components, are planned and simulated. In Omnet++ on the right side, the pure network simulation takes place after the planning data has been imported from plant simulation. The network can be then tested according to the configuration. To ensure that the co-simulation also calculates with the latest data, changes of the HV positions, status of the machines, and also the network load are exchanged via a bidirectional connection. In our project, a concept has been developed which covers all necessary steps from the data origin to the simulation process, in order to give an early prediction of the industrial communication network. And in this short video, we can now take a closer look at the co-simulation and visually observe the exchange of information. Depending on the utilization state, the sphere changes to a corresponding color and signals the utilization of the communication component to the planner. In future work, we still need to make some adjustments regarding the simulation and perform a following validation. Thank you for your attention, and I'm happy to answer your questions. Yeah, hello to the question and answer session, and you can always send me your questions right now. The first question is, will the factory of future still use wired data connections or just fully wireless? Well, this question is not that easy to answer because we don't know in which direction the future technologies will go. For example, current technology like 5G or Wi-Fi 6 are currently not able to fully replace the wired connections. So at the current state, no, we are not able to fully connect wirelessly to the factory of future, but maybe with future technologies, Wi-Fi 7 or maybe also 6G technology, we will be able to replace the wired connections and therefore be more flexible. We have another question here: how can communication networks keep up with the ever-increasing data volume and communication needs of IoT? For example, transfer of high-frequency data to cloud. Yeah, I think that's the biggest point of the further new technologies. For example, 5G is giving more and more data throughput, so we are able to transfer more and more data. And there will always be a challenge between current technologies and future technologies, and therefore I think the technologies will always keep up with the increasing requirements of our current networks. So therefore I'm not worried that the future technologies will be able to suit or to be able to keep with the requirements. Do we have some more questions? Okay, what are solutions for factories in the countryside without 5G networks? So solutions for without 5G networks, if you want to go wireless, maybe in the future we are not able to implement it yet, but in the future there will of course be Wi-Fi 6 as a replacement for 5G networks if you don't have a 5G network, because it's quite expensive to implement or to replace a Wi-Fi network through a 5G network. So you have always to look at the infrastructure holistically, and therefore you're always or you're able to implement a Wi-Fi 6 network, for example, if you don't have the 5G network, therefore. And of course always the wired infrastructure also. Another question: what is the scale of simulations? Are we able to create a simulation to create any fully functional factory? So I think you mentioned the simulation of which you have seen before. So the current simulation is able to, at the current stage, to simulate around about 50 machines. So I didn't test it with more than 50 machines, but at some point we will have some performance issue to do it in real time or to do in increased real time. So therefore we have still to do some performance testing, therefore to see how many machines at the same time we can address at the simulation. Are there any communication faults? Yes, of course. We are also simulating communication faults. For example, if the communication partner or the communication device is not available, or also if you have package losses during the transmissions, everything is at this place what Omnet++ gives us also simulated at this point. are security consideration part of the simulation somehow? Not at current state, because also security is not that easy in the industry currently, for example with Profinet, and therefore we are currently not considering security at this point. But of course, if you look in the future, it's a possible direction where we can still provide future simulation or also future work, therefore. Yes, I see no one has any questions left, so then I would like to hand over to the moderation part. Thank you for your questions, and you're always welcome to ask me any questions.
Now, thank you, Petar Vukovic, for this very nice presentation. From platforms and planning, we directly turn back into the lab, and I'm really already very excited about what Sebastian has prepared for us in the next part of the virtual lab tour. So back to you, Sebastian. We're looking forward to it.
Welcome back in the lab. I'm still so happy that so many parts of our first demonstration worked well. Hopefully, we can continue like that and have a nice second block. Yeah, planning and platforms. That's part also of the first station of our lab tour. I want to show you in the first minutes of the second block. Over the last years, we had autonomous guided vehicles, HGVs, driving around factories, getting rid of those inductive lines in the floors, and somehow moving from rails, literally, to a free navigation. And one key research ever then was the research on platforms for the interoperation of different systems. Several years ago, all the ecosystems for autonomous guided vehicles were closed ecosystems. So we very often found the situation that we had manufacturing systems with several platforms and several software stacks operating side to side, because there was no connection and no standard for the interoperation of autonomous systems from different suppliers. And when you found the perfect setup from supplier A for your payload, for your sensors, whatever, you started with that supplier, and maybe at some point you found out that you need a smaller or a larger system, and then that was a system your supplier wasn't able to offer, and you had to go to another supplier of HGVs, and most of the cases you then also had to install their fleet management system. Luckily, that changed, so we now have a new VDA 5050 that gives you a guideline how to design the interoperation and the communication between HGVs. So now we are seeing many platforms that allow what several years ago only was possible in our research to really connect different systems. So what's next in terms of those platforms? Well, now that the systems can communicate, it would be time for really interconnecting them and integrating them in one larger approach. And in a recent project here, we were able to create a middleware that not only enables the connection and the planning between HEVs, but more or less did form a complex system that was somehow self-regulating. How did we do that? We had a approach where all the vehicles were agents, and they knew about their different parameters like payload, speed, their position, and on the other hand, we had a kind of marketplace for transport tasks. And then it was not only like it is in our cities, at least in Germany today, that you could call a taxi and it was one taxi operator and no interaction at all, but it was more or less a distributed system where all the transportation tasks afterwards were rated. So maybe you had one unit like this system here, and it bid for transportation tasks in the market, and it always was quite optimistic or even too optimistic, let's say, in terms of its transportation speed. So it offered its transportation task, it won, and then it failed the deadline it granted. And with our system afterwards, it got a bad rating in terms of the low speed. And the systems use those ratings to slightly adapt their internal parameters. And when you do this in a fleet with a size large enough, then you will soon get a kind of self-regulation over time, because too optimistic systems will reduce their bidding of optimism and vice versa. And thereby, the next step we see is not only communication, but integrating them in one system that together forms new complex behaviors. This was one research area, and the second research area still ongoing is the cost-effective realization of autonomous vehicles. So over the years, we developed quite a number of systems. You can see some of them in the back. We had nice projects together with other large companies, and there were different approaches to reduce the price. One approach was to simply build very, very small HEVs, and then you could get rid of all the performance level D or whatever sensor systems, because they were that lightweight that even at full speed they could hit you without violating normative regulations. Of course, this approach is very limited in size of goods you can transport. And second approach we saw was to not always start from the scratch, but to use standard parts like weight sensors, like batteries. And by this approach, even while integrating safe sensor systems, reducing the cost. And this is not the end of the research on autonomous vehicles, because even if you integrate a sufficient set of sensors for the application of intralogistics indoors, you will soon find systems, or you will soon find the need for systems that could interconnect also different facility, different buildings in your factory, for instance. And one example is here standing next to me, a large system, for example, doing milk runs. And our research approach here is a cost-effective and adaptive integration of different sets of sensors to be able to not only drive indoors, but also to interconnect buildings. Imagine it's in winter, you have your warm factory building, and then your door opens, you drive out in the snowstorm, the blizzard, and in the next building, again, you change from minus whatever to plus 23 degrees. And then you don't want your visor of your camera get fogged. And also the regulations for driving insides and outsides in terms of allowed sensor systems is different. So what you need to do such a task is a system that can dynamically reconfigure its sensor set to always be safe, but to adapt to the weather conditions and the scene where you're driving inside or outside. So we will see new things in terms of mobile systems. And recently we connected those mobile systems with manipulators. And then we had the capability to do complex tasks in different locations. And following this approach, we had the need for an intuitive interaction with those systems. And this will be the second setup I want to show you. So I have to walk a little bit, and you can follow me while we switch the camera to the new location. As I already said, the project I'm showing you now is derived from mobile robots, and the very scenario you see here is not mobile robots, but it's robotic systems for the handling and sorting and cutting of nuclear waste. So again, something where a robotic system can be very capable, but it's challenging, and of course here, not only from normative regulations in terms of fences or whatever, but also because of the application, you are not able to really interact with the robot, but you want to do complex tasks with such a robotic system. And in this use case, the task is that you have a 200 liters bin of radioactive trash. You put all the stuff that is in the barrel onto a sorting table, and then you first want to sort everything that's in there. And as radioactive waste was stored over the decades, it can be very different what you find in those barrels. So you have to sort it, and then you have to characterize it, maybe even cut it, and put it in another barrel. A really complex task, and a future goal is that robots will be able to do this automatically. If we switch here, you see a very small video stream. It's not very essential what parts are picked here, but what you see is the autonomous grasping of different things the robot doesn't know. So state of the art is grasping of known things. You can identify them, calculate grasping poses, but for unknown items, you will very soon find when you open those stored nuclear barrels, it's very challenging to enable a robot to do a sorting task completely autonomous. And here, what we call augmented virtuality comes into play. So we enable a teleoperation personnel by virtual reality to teleoperate those complex manipulators. And of course, it is easy to render all the known parts, the robots, the table, whatever, but by sorting trash, you will have different parts, and thereby the augmented factor comes into play. We use different sets of 3D cameras and other point cloud generating devices to enrich the scenario and to enable a teleoperator to interact with all sorts of varying goods and parts. And I will now try to shortly show you this. So I switch the perspective, and on the screen you now see what I will see when I'm wearing those VR gears. So I put them on, and after a short while I see the virtual scene in front of me, and I now have two controllers, and by enabling one controller I can freely move one robot, or what's nice in this setup, I can even in parallel move those two robotic systems. And if you look closely, unfortunately, those VR stuff is maybe something you will really need to experience when you visit us at our lab. But let me tell you that the projection quality, if you do nothing at all, only use the raw data, is quite limited. So you can see those dynamic objects, and what I can try to do is at least to a little bit interact with it and at least make those small ventilator fall, but the display quality is not that good. And we have two approaches in our research. One is using AI systems to identify objects, re-identify objects, and then not display the raw point cloud, but to then render a CAD model. And a second approach developed by our partners in this specific project from the company Framatome is to use stereoscopic real-time video displays which are collected for each eye. So this is only something I can tell you, but for this improved view, you see now I have a sensation of depth, so I can also estimate how far objects are away. And in this visualization, it's very easy to even identify smaller parts and to do somehow critical or difficult tasks. So, yes, now I was also able to wear a VR gear as we had it for several times. And this is more or less the end of our lab 2. Thank you very much for attending it. And I will now switch to our discussion room and be available for questions at the end of the session. On behalf of my colleagues, again, thank you very much for watching this, and see you soon.
Another very impressive demonstration. Thank you so much, Sebastian. Well, in the final part of today's event, 2 other exciting research projects await us. Martin Sjarov will elaborate on the topic of end-to-end data integration for additive manufacturing. And Siemens FAU PhD student Benjamin Lutz reveals a solution approach for in situ identification of material batches in metal machining. So please, Martin Sjarov, the stage is yours.
Hello and welcome. My name is Martin Sjarov and I'm a research assistant at the Institute for Factory Automation and Production Systems at the Friedrich Alexander University. So in the next 5 minutes, I want to briefly introduce my research project together with Siemens, and it has the working title End-to-End Data Integration for Industrialized Additive Manufacturing. So we're in the domain of additive manufacturing, and they're specialized to metal additive manufacturing, but the overall thoughts are valid for any kind of additive manufacturing. So typically we divide the additive manufacturing process chain into the pre-process, the in-process, and the post-process. Within the pre-process, we have activities such as the part design, simulation activities where we simulate, for example, thermal inferences on the final part. We also construct support structures to support the parts throughout the actual print process, and we prepare the actual print job using different parameters. In the in-process, the actual build process in the physical machine happens. There we construct the part layer by layer, fusing metal powder using laser energy. In the post-process, we have activities such as the depowdering of the build job and the parts, the removement of the parts from the build platform. Maybe we have some other surface finishing, and then in the end we have the quality control where we, for example, acquire 3D scan data or CT data or other material properties. So regarding this process chain now, the question arises, how can we bring together all the data that is produced or generated throughout the entire chain? So how can we realize some end-to-end digital data integration? I will explain our approach using some kind of generalized architecture here. So we would reduce the actual process chain here to the physical process, and on top of that stack some layers where we fuse the data occurring along the process chain. So at first we have different specialized applications along that process chain that are or need to be used and that can generate the specialized data for the process steps. So for example, in the pre-process, we typically have the computer-aided design, we have the simulation activities, which are summarized as CAE, and we have the support and build job generation within CAM activities, which would, for example, be realized using Siemens NX. Then coming to the actual in-process, we have the process execution trigger and the build job files, and we can receive, for example, using integrated sensors or using edge devices, process data. Then in the post-process, we also have some process execution triggers, and we can also acquire process data, and using the quality control, we can acquire quality data such as 3D surface scans or CT data or material properties using material inspection. Then to bring together this data which occurs in these sources, we would stack on top of this some kind of integration layer, and there the research approach is to use knowledge graphs to bring together the data from the different specialized software. To do this and stack on top of this overarching applications such as dashboarding or KPI generation, at first we describe the domain, which would be the additive manufacturing domain, and secondly we would describe the different data sources using the knowledge graph, and then federate the occurring queries from the applications to fetch the data which is needed to answer the different questions or queries which arise. So to summarize this project, we use this generalized architecture to realize end-to-end data integration to answer questions such as how quality data relates to actual product PMIs or tolerancing information, and how additionally to that process data can be related to this PMI and quality data. To realize this, we use knowledge graphs to describe the additive manufacturing domain and to describe the data sources along our process chain. And then we use this generalist architecture to implement a web application where we realize different use cases. Okay, so that was it. Thank you very much for your attention. And now we are ready for the next talk or for questions. So, I'm happy to answer the questions in the Slido. I see one question. Will there be specific knowledge graphs for different AM processes, as for example, wire arc and additive manufacturing, or LMD, or a generic one applicable for all? So, interesting question. The concept of constructing graphs has an advantage that you can add more information to your existing graphs or combine or load several graphs together. So I think it will be an approach where you, of course, will have some top level descriptions, which will of course be quite generic, which is or what is identifiable, that we have some common set of vocabulary that we will definitely need for all of additive manufacturing, and then we will need some specializations for different kind of processes. Personally, the project I'm involved with deals with laser powder bed fusion, so currently this is our focus. And yeah, I think it will be a modular approach with reusable top-level graphs, and then you add the specifics that you need to integrate some specific data. So, are there any other questions in the Slido chat? If this is not the case, this is not does MindSphere support this system? Actually, the approach we're researching right now is independent of platforms that are developing themselves at the moment. So to do independent research, we are independent from MindSphere or other platforms. So if MindSphere supports this, actually, I don't know exactly, but we are currently not on MindSphere or using hardware software involved with MindSphere at this moment. So the next colleague ready to present is Benjamin Lutz, and I happily hand over to his next project pitch.
Hello everyone, my name is Benjamin Lutz. I'm a PhD student at Siemens Technology in collaboration with the FAPS Institute, and today I'd like to give you a quick introduction into my latest research. In my research, I'm looking at metal machining operations such as turning and milling operations, and when talking to practitioners in the field, we noticed the challenge of machinability deviations among material batches. So what is that all about? Well, the raw material that is used in such facilities is normally produced itself in a batch production process and supplied from multiple vendors. So what that means is that the material that's arriving at our facility is coming from many different vendors and many different batches at these individual vendors. And as every technical process has some fluctuations, these batches differ. For example, they might have slightly different chemical compositions, the fabrication procedure might have been slightly different, or there might be deviations in the heat treatment. And all these different effects lead to deviations in the machinability, how well a material can be machined among these different batches. So that means that some of these material batches arriving at our facility might be really easy to machine, whereas some others might be really hard to machine, which could mean that the tools break early and that the process might run really unstable. The issue is that on paper, all these materials adhere to the same specification. So we're really talking about intolerance deviations. And what that means is that we cannot assess these deviations prior to machining, but these deviations are typically only noticed throughout operation. So what can people do to combat these deviations in machinability? Well, a naive approach would be not to consider these deviations at all. Thereby, one would just choose a generic set of cutting conditions that can be applied to all type of material batches encountered. Thereby, of course, one needs to select rather conservative cutting parameters to also account for material batches that are rather hard to machine so that we don't have an early tool breakage. And therefore, if our material batch is actually really easy to machine, we're wasting a lot of potential, therefore increasing the production costs. Another approach would be to tighten the tolerances on our material specification, thereby limiting the impacts such deviations might have. The downside of that is that thereby the production costs for the actual material might rise as there are more strict guidelines to adhere to, and we might limit the number of suppliers who are capable of providing the material we need. And lastly, what you can do is you can just test every material batch arriving at your facility and carry out extensive material characterization to really find out what the exact machinability is like and how to machine it in an ideal way. Thereby, you can ensure that the process runs at the ideal conditions as you have the lowest production costs, but of course you have really high material testing efforts, and therefore this approach is typically unfeasible in production. So as a solution, we're proposing, instead of doing this material characterization as a prior to machining operation, to carry out material characterization throughout machining so that we can load our machine with any type of material, and the machine itself will find out how the material, what the machinability of the currently machined material batch is like, and how it can be machined in an ideal way. And thereby, we can ensure that each material batch is machined at its ideal condition. So what does this solution look like in detail? Well, an important aspect in process monitoring for subtractive manufacturing is that you need to know the condition of your cutting tool, because the condition of the cutting tool is significantly influencing the signals you can observe. Therefore, we're introducing a visual tool condition monitoring system into our approach, consisting of a camera that is integrated into the machine tool, and then at regular intervals, the cutting tool is positioned in front of our camera, an image is taken of the cutting tool and analyzed during a neural network. Here, we're using image segmentation, which means that for every pixel in our image, we try to find out which defect class it belongs to, thereby, contrarily to classifying the image simply in serviceable or worn, we're able to really find out which kind of defect is visible, how large the defect area is, and what the shape of the defect looks like. And thereby, we get great detail of wear information about the condition of our cutting tool. To implement such an approach, we're investigating the usage of convolutional neural networks, which have been proven really successful in the area of computer vision. A challenge in machine learning, of course, is always the scarcity of training data, especially in supervised learning where you need pairs of raw images and annotated images. A lot of effort needs to be taken to generate these training data sets. And here, as we're talking about industrial applications, publicly available data sets are typically scarce, so there is no other data from outside you can really incorporate. Thus, we're investigating the usage of synthetically generated data using generative adversarial networks to artificially enlarge our training data set by creating data from scratch. And thereby, we're able to transform data from other domains to a new scene in the tool condition monitoring system. And we showed that using such an approach, we're able to reduce our labeling efforts by 2/3. So with the tool condition assessed using such a visual tool condition monitoring system, we can now jump back into the material batch identification procedure. Therefore, we're using a Z-numeric edge device, which is connected to the machine's numeric control. Through the edge device, we're now able to acquire internal control data from the machine tool at a high frequency of 500 Hz. This data includes, for example, the commanded axis position, the actual positions measured by the encoders, the current, the torque values for all the feed and spindle drives. On the edge device, we're also running a data pre-processing routine, which is aggregating this continuously acquired data into information-dense features. Furthermore, we're running the classification approach that can then find out which material batch is currently being processed. What does that look like in detail? Well, for the data pre-processing, we're using a sliding window approach where we're separating the continuously arriving data into windows of 1 second lengths. For such a window of 500 values, we can then condense the continuous data stream into a few features, such as the signal's means, the standard deviation, but also more advanced features. Thereby, we're able to reduce this raw signal coming from the machine tool into a very condensed feature vector. Now we can use these feature vectors to train our classification approach. Therefore, we conducted cutting experiments where we measured the process data acquired from the machine tool and parallel acquired the ground truth data about which material batch is currently present and being machined. And using these pairs of observed feature vectors and actual ground truth material batches, we can now try to train a supervised classification model to derive this mapping between the feature vector and the material batch. And this model can then be used in operation to predict for a new feature vector which historic material batch it is the most similar to. And here we investigated different algorithms such as support vector machine, random forest, and artificial neural networks, and found that all of these are really successful at identifying these different material batches. The whole approach is implemented using cloud and edge computing technologies. We're using the cloud mostly for model training, such as these image segmentation models, as they really require a lot of computational power. We also use the cloud for visualization of the target metrics, such as the detected tool conditions and the identified material batches, so that a technology expert can assess all these metrics without having to go to the actual facility. Also, the cloud is used for the control of the edge device. On the edge device itself, we're running the actual inference models, so we're analyzing the image data as well as the time series data. We're running the data pre-processing modules, and we're also running dashboards. The operator right next to the machine can get these insights into his manufacturing process. So with that, I'm reaching the end of my presentation. Thank you very much for your attention, and I'm available for any questions. Thank you.
Okay, are there any questions? Let me open that. So there's a question, can the approach also be easily transferred to other processes? Yeah, so if we think about this identification of influences of batch effects, that can definitely be transferred to other processes. And I mean, a first requirement would be that there are influences of material batches. And if that's the case, then one would need to sit down and find out what kind of data is there available. Now, for example, if we're looking at an additive manufacturing process, we, for example, might have like influences in the powder that's being used. Then we can definitely use a similar approach of like trying to figure out how these influences can be seen in the data we're acquiring and how we can use that to train a model to identify these influences and then predict that material batch and to do some corrective actions. And also, if we look at the image segmentation approach, that is already being transferred to other approaches, for example, in defect detection for different applications. Okay, another question would be, how can the accuracy of the algorithm be further increased close to 100%? Well, first of all, the question is whether 100% is really the main target, because in this question, as we're talking about differences in machinability, there might be materials that are from different batches, but actually behave rather close to. It could be that in these cases, if two material batches are different in behavior, but behaving still similar enough, then the misclassification among those might not be too bad, as you're basically classifying them as the next best candidate. So the question isn't really to reach 100% accuracy, but to reach the parameters that like would always give you the best cutting parameters, so you can manufacture the material as good as possible. To reach a better accuracy, though, one would need to first of all, like with any machine learning approaches, increase the training data set, look at more diversified training data, such as different tools, different cutting conditions, and thereby just have the model train on a broader variety of data, and thereby increasing its predictive capabilities for operational use. Okay, let me wait a second if there are any other questions. If that's not the case, then thank you for your attention and all the questions.
Thank you, Martin Sjarov and Benjamin Lutz. What a spectrum of different joint research projects, and what an exciting journey through the factory ecosystem of the future. We are almost at the end of the lab tour, but before we close today's session, we would like to announce a few more exciting events of the Research and Innovation Ecosystem Event Weeks 2021. And of course, as promised, we will address your remaining questions concerning the lab tour after the brief announcements. Coming up next week on Friday, October the 22nd, we will have another special online event, the Siemens FAU Research and Innovation Ecosystem Conference. The event will be streamed online live from the Open Innovation Lab Joseph's in Nuremberg. Don't miss the opportunity when CEO of Siemens Roland Busch, Professor Jörg Franke, Head of FAPS, Dr. Marina Wallisch, Siemens Vice President Service for Factory Automation, and Professor Alexander Martin, Director at Fraunhofer IIS, will share their perspectives on the factory of the future. In just a minute, I will show you how to register for this event, if you haven't done it yet already. Following our conference next week, an exciting Siemens Digital Tech Talk from the Siemens factory in Amberg is right around the corner on November the 8th. And last but not least, RWTH Aachen will start their Siemens Research and Innovation Ecosystem Week on November the 4th, also with a virtual lab tour. For all the events, you can register via the website that awaits you behind the QR code you're about to see on the left side. And as Professor Franke mentioned in the beginning, if you want to learn more about our Institute for Factory Automation and Production Systems at FAU, you find more information by scanning the QR code on the right side. All the links, of course, can be also found in the YouTube description of this event. Now, enough from the announcements. As promised, we turn our attention back to the remaining questions before we say goodbye for today. So I kindly invite Sebastian Reitelshöfer back to the stage and his colleague from the lab tour. So please, in case you have any further question, ask.
Yep. Sorry for that. So, if you have any questions, feel free to ask us now. Oh, da löst sich das Mikrofon auf. Easy. Okay, so now I also see the questions. Yeah, thank you for the first question. We have different projects together with Siemens, and we are, for instance, investigating how to create new electronic production systems. And there we are not only cooperating with technology, but also with different factories here in the region. And there's a second question. The question is, in how many years can the use cases shown from the lab be seen in live production? Well, that differs. I think the autonomous guided vehicles are an everyday product, so you can see them right now. And I think in a near future, it will be possible to also have more advanced fleet management systems for the flying robots. Maybe I can forward this question to my colleague Markus for his estimation.
I think for the autonomous flying robots, it will take us around about, or at least 3 to 5 years. On the one hand, of course, there are regulatory questions that we need to address, and on the other hand, there are various technical problems that need to be solved.
As I said during the lab tour, we need to address the redundancy. We need to address the aspects regarding environment perception, object interaction. So it's not only a case of regulatory problems, but also different technical aspects need to be addressed.
Yes, and I think for the last use case, we show the teleoperation that is also more or less being used in early stages right now, but it's only, I would say, niche applications, and a broader distribution of capable autonomous systems that need that form of interaction probably are also several years ahead from now. So the next question we see is, will the future of intralogistics be purely automatic? I think not in a nearer future, at least, because there is, at least up to now, always a challenge when you switch from your autonomous system into the machine, into the process. And I think there is also a lot of research needed to be done to close the gap, because it doesn't make sense to have a completely autonomous material flow and then you have persons unloading load carriers. So there are gaps, and I think it will take us quite some research to get automatic or autonomous systems that are capable of closing that gap and unloading different parts in a cost-efficient manner. So the next question is for drones, so I would just hand the microphone over to Markus.
Thank you very much. The next question is, do you think we can operate autonomous drones with augmented reality? Of course, this is possible. There's also already many research going on in this area. But if we think of industrial application, to operate drones using augmented reality has rather a minor benefit. Within industrial operation, we actually need the full autonomy, because whenever the drone needs to be controlled manually, we lose a part of its efficiency. It costs both time and money. So for the autonomous warehouse drones, of course, we aim for a fully automated, fully autonomous system, and not for augmented reality control or a virtual control. I think the next question can be addressed by Sebastian.
Yeah, thank you. The next question is, do all 8 research groups under FAPS have research taking place with Siemens? I think it should be like that. Up to now, it's probably not completely fulfilled this goal, but I think all the 8 groups have the potential to cooperate with the broad spectrum of Siemens. And at least for my group, we have 2 ongoing projects, and one more or even another one more would be, of course, nice. So, and there's another question, does FAPS have any webinars or workshops to benefit the research community? Yes, we try to do it regularly. So we have different forms of technology transfer. We have seminars. Of course, the last 2 years, those seminars were also online. But hopefully in the next year, we will have our montage seminar where we can discuss on handling and automation tasks. And then we have different other platforms like the FAPS seminar. So if you're interested in that, get in contact with us, and we can forward you invitations and information on our different platforms and activities.
Now it's time. I have to thank you for your interest and your active participation in today's event. We hope you really enjoyed it. We definitely did. I also have to say a huge thank you to Professor Franke and his team, especially towards Jonathan Fuchs, Sebastian Reitelshöfer and Matthias Brossock, who have co-organized the event, as well as towards Petar Vukovic, who managed the entire streaming. Great job. So now it's time to say goodbye. Take care and see you next week at the FAU-Siemens Research and Innovation Ecosystem Conference. Have a great night. Bye.